we talked about, okay, well, how do we develop a floating point system? And we talked about the fact that unfortunately rounding and special values, which in this case zeros, infinities, not a number, and to some degree subnormals, they just kind of are useful things. Like often the other solutions are worse. So I'm now going to try and talk a little bit about the SMT theory of floating point. So this is standardization of a standard. So links. IEEE 754 is the standard that specifies how floating point should work. So the relation is that most modern hardware, certainly at the sort of large scale things you work on, implement IEEE 754. So ARM does, x86, Spark, Power, MIPS, all of the main CPU architectures. Then you have things like ISO 9899, which is the C programming language standard, and they mostly use this and reference into it. So there's an appendix in the C standard that says C has a float type and a double type, and we haven't really told you what they are, but if you implement appendix, I think it's C or D, then they are IEEE 754 float 32 and IEEE 754 float 64. So yeah, that's there. And then what we're doing here is we're trying to formalize that standard. So one of this kind of alphabet soup, but the end result should be that if you wish to reason about hardware, or you wish to reason about the programming language, then using the formalization in SMT-LIB should be sufficient. So, throw back to a couple of hours ago when we were talking about theories. So, how do we actually specify one? We need to fix the signature. And those are the theory files. You remember when I clicked on the website, we had a list saying theory, one of them is floating point. That is the syntax for the floating point theory. That's how you write a floating point add. That's how you write a floating point constant. And that's defining the signature part. That's the same as the heart and the club, or the plus and the plus there. The other thing we need to do is we need to fix its interpretation. So most of the SMT-LIB theories, the interpretation is actually described in the theory file itself. Floating point's a bit of an exception just because it's maybe we're tied with strings now, but it's the largest and most complex of the theories. So we actually have the semantics in a separate document. So what I'm going to do is just kind of run through a bit of how that semantics works so you can actually make sense of it if you need to implement it. So first off, the domain. So this is a screen grab from, as it says up the top, IEEE 754. And it says that the standard actually talks about floating point at basically 4 different levels. So it has a concept of extended reals and a concept of extended reals plus not a number. And again, this is where you need that to make it algebraically closed, because otherwise what's infinity minus infinity? We formalize roughly at this level. So we've got sign, exponent, significand, positive, negative. We only have one nan. Notice also the difference between level 2, we have the 2 zeros. Level 1, we only have 1. So it's really this sort of level we're at. What we don't do, and this is deliberate design choice, is we are not formalized as bit vectors. So although we use bit vectors, a floating point operation is not, this is what it does to the bit vectors. That is not their semantics. And sorry, this is deliberate, and it's deliberate because if we formalized it just at the layer of like, actually these fancy bit vector instructions, it really limits what you can do, how smart you can be about writing new decision procedures. So for us, we have the extended reals, which is the level 1 part. We have the floating point numbers, and we have bit strings, which is the level 4 kind of view. So examples. If we want to write 1.0 single precision float, we write it like this. So this really is the bits that you would have in memory. So if you're writing a program analyzer, any kind of tool like that, you really can just go from this bit string straight into and out of memory. Early on, people wanted to be able to write sort of, 10 and have constants that were human readable. This turns out to be a real nightmare, because there are constants like 0.3. Well, obviously 0.3 is, it's 3 divided by 10. You can't represent it with a binary number. So when you write 0.3, actually what you get is not 0.3. It's something very close to it, but it's not. So the point is that decimal strings can describe an awful lot more floats than we actually can represent. So the representation of constants is bit vectors. So that's our domain. Then we need to talk about the interpretation of the symbols. This is our map. This is what does the heart symbol mean? So this is the really key bit from IEEE 754. Each of the computation operations that return a numeric result specified by this standard shall be performed as if it first produces an intermediate result correct to infinite precision and with unbounded range, and then rounded intermediate result if necessary to fit in the destination's format. So that's kind of our guiding principle of how this should work. So what we have is we have the level 1 formalization, which is the extended reals. So this is reals plus an infinity at either end. And then we have the floating point numbers. So each one of those is a bit string. So this is kind of like I was saying at the start about you've got your line of reals and you've got your bit strings. And each bit string is associated with a value, a real value. You've got your 2 zeros, so you can determine convergence. And we've got a map. In this form, in formalization is a map V, which takes you a floating point value and gives you a real. So because the map V is monotonic, you can think about the adjoints. So when I was looking down the general chat, I noticed there was someone who was saying about Curry-Howard isomorphism. So yeah, adjoints. This is as close to category theory as we get. And so basically you can say V maps from bit strings to extended reals. Therefore, we've got a map V over bar, V under bar, which take you an extended real and give you the smallest float that maps above it, or the largest float that maps beneath it. And so really central to this idea is that the concept of rounding. Rounding, you are picking one or other, your rounding mode picks one or other of those adjoints. And so the semantics for almost all of the floating point is basically take your float, work out what it is in extended real, do the operation in extended real, and then pick one or other of the adjoints to round it back, which is exactly what the standard says it should be. So how does that actually work? So syntax, we've got fp.sub takes rounding mode, 2 floating points. Notice that in the standard floating point is parametric. You can say how many significand bits and how many exponent bits you've got. Takes 2 of those and gives you back a floating point. So that's all in the theory file because that's fixing the signature. Then the semantics, what's the interpretation of fp subtract? Well, what you do is you take f and g, you use v, you find their value, and this is an extended real, you subtract that, and then this lot is basically pick one or other of the adjoints and apply it. And there's some detail about if you subtract 2 things and they cancel, what sign 0 do you get? And so all of that, that's fixing the interpretation. So this is why we're doing SMT, fixing the interpretation. And so what you actually practically write to the solver is this: fp.sub, whatever your rounding mode is, end and start. That's from our program. Predicates work pretty much the same, equals, less than, or equals, is less than, you get Boolean, and all they do is just go, well, what value does this bit string represent? Is it equal? Notice that this will make the 2 zeros equal. Is it less than? Okay, take the 2 things, work out what its extended real value is. So you just test the equality like that, less than, so that I think is the termination condition for our program. Actually, no, it's one of the early guards. You're saying, is this less than 0? That's so end minus start, whatever rounding mode you're using. Yeah. So putting it all together. So from the program, we have this, which is quite key. It's working out how big our increment is. N minus start divided by n plus 1 plus a floating point 1. So it's a floating point divide. And literally, we can convert it like that. We can convert it like that. And when we run it through a solver that's got this implemented, we will get back the same results the hardware should give us. Right, but that's assuming that we've got it implemented in the solver. So how would we do that? So this is something I alluded to earlier with the question of, well, how do you come up with decision procedures? And I'm tempted to quote one of my students who once said something very, very smart to me. And he said, like, the thing about abstraction that everyone gets wrong, people think about abstraction in terms of what information you want to keep. And he said, don't think about it like that. Think about abstraction in terms of what information are you okay with throwing away? And that I find is a useful viewpoint. And so if we want a decision procedure, well, what do we know about floating point? So we know that it's possible to come up with hardware implementations of it. I mean, that was kind of the point. So the fact that we got hardware implementations, that means we can build a circuit for it. If we can build a circuit for it, well, we could convert it to the theory of bit vectors. And then if we've got a bit vector solver, we could solve floating point. That's pretty cool. Yeah, okay, so that's one route. We know that it's monotonic weakly. So, you know, if you've got A less than B and you add on a constant, then A plus constant and B plus constant. A plus constant will be less than or equal to B plus constant. It's one of the few properties that's really strongly maintained by floating point. And so if we've got weak monotonicity, if we throw away lots of the other stuff, we can think about, well, can't we do this with intervals? The fact that we've got formalization, well, that means we could do some kind of axiomatic kind of approach, because we could just use that formalization. You know, if you've got a real solver, then we could take this, translate everything to reals, and we could put that into the solver. I mean, it's again, it's a translation approach, but it's possible. Then also, we know that we've got fast implementations. Could we try and just do some of this numerically? And it turns out that these are the kind of sort of 4 main threads of how people build decision procedures for floating point. So bit blasting. Yeah, so as I said, basically the idea is if you've got a circuit for a floating point adder, you can turn that circuit into a bit vector. The bit vector solver can turn this into SAT, and this is the link with Armin's talk. You can build SMT solvers that contain SAT solvers. If you convert your bit vector problem into a SAT problem, you can then solve it with the SAT solver. So if you can convert your floating point problem to a bit vector problem to a SAT problem, job done. And it's quite easy to implement on top of the bit vector solver. You just need to do the translation. Unfortunately, doing that translation is not easy, like writing the code that does the translation. And I'm going to talk a little bit about the library that I've written for doing this. And I deliberately wrote it as a library because it's not an easy task. It's not an easy thing to do. And I kind of wanted to save other people from having to do it. So implementations, CBMC, I think, has the first implementation of this. Then C3, MathSat has an implementation, Solar, CVC4 does, and recently Bulector, which is now known by a new name, Bitwuzler, has also acquired a bit blasting implementation. Intervals. So this is this idea, if you've got positive S and you add it on, then A plus S is less than or equal to. So what this means is that if you've got intervals, you can add intervals, you can do interval arithmetic. And this is a really fun technique. And there are a number of different takes on this. So Colibri are, in terms of the competition, Colibri are probably my main sort of competitors. And they're great because they just implement such a different take on this. They are very much an interval tool. They don't currently have a SAT solver. So commonly you see SMT and SAT solvers talked about together. They're quite different tools. Now, a lot of SMT solvers contain or use one or more SAT solvers, but not all of them. And Calibri is a lovely example of people just doing completely different thing. And they do some very, very smart stuff with intervals and interval propagation. FPCS, if I could ever get my hands on a copy of it, I'm told is brilliant. It's just hard to get. Number of years ago, we wrote quite a well-cited paper on a mix between this kind of interval reasoning and clause learning, which was implemented in MathSat. That's exciting stuff. ISAT does something similar. Then there are a bunch of abstract interpretation tools which do, they're more focused on programs rather than formulae, but they do similar, internally they're doing similar kinds of things. Axiomatic formalization. So most of the interactive theorem provers, Isabelle, Hole, Koch, ACL2, this kind of thing, most of them have formalizations of floating point. The problem with most of those is that they don't necessarily have decision procedures that work with them. I should add lean to that list as well, probably. However, there have been a number of SMT solvers that do this kind of axiomatic approach. Altergo is probably the most active and most useful of these, and they have a sort of formalization of float that turns the problem into reals, and then they try and solve it as a real problem. And again, that's really nice because it's just having that sort of diversity of different ideas and solutions. You find there are some problems they find are really, really easy and they do way better than us. And there are other problems that we handle really well. So then there are people doing sort of numerical approaches. And the idea of like, well, look, you know, if you've got a GPU on your machine, you can do a lot of float calculations very, very quickly. And so you don't really need to know directly too much about floating point. You can use kind of black box search techniques. And in principle, you can find counterexamples very, very quickly. The first one of these was called XSAT. We compare against GoSAT, where it actually compiles the formula down to executable code and then kind of does a brute force search over the executable code. JFS does something similar. In principle, this approach should work really, really well. On some restricted benchmark sets, it does work really well, but every time we've tried to like run this sort of thing at scale on larger sets of the SMT-LIB benchmark collection, we've never got particularly good results, even using a number of different tools. I don't entirely know why this is. It feels like the kind of thing that should be doable. Somebody should be able to make a really, really strong solver like this. Just hasn't happened yet. So that's the sort of overview of the kind of 4 big areas. And now I'm going to specifically talk about one of the ones I've been working on, which is a bit blasting approach. So I'm going to take the float, I'm going to produce the circuit that does that computation, and then I'm going to hand it over to bit vectors. So
there is a question which asks that whether the numerical solvers are based on local search based approach.
Yeah, there are people doing local search type things. Off the top of my head, I can't remember which local search algorithms they use, but yeah, it's very, very much that kind of thing. As in, you assign a concrete numerical value to all of your variables, you run the formulae, and then you assess how that could be better or worse. You know, you assess yeah, should we increase these values? Should we decrease these? There are a few bit vector solvers that do something similar. Yeah, if you really know local search well, it feels like it feels like that people should be able to build solvers that do this kind of thing really well, but so yeah, SymFPU. It's a library. It's a C++ library, and it is parametric in terms of how you represent the bit vectors, how you represent individual propositions, how you represent rounding modes and these kind of things. And so the idea is that you can plug this into various different solvers. And at the moment, I wrote the integration that connects SymFPU into CVC4, and it's used as CVC4's floating point solver. This might be a rash claim, but I'm going to claim that it's actually reasonably well optimized. I spent quite a bit of time on this. It's not, you have to be a bit careful because if you just sort of go and look up what's a good floating point circuit, you'll get a lot of things that optimize for things that hardware needs. This is not the same as what makes a good bit vector encoding. Some of the tricks carry over, some of them work, others don't. And so there are things that you need to optimize for in hardware that just aren't relevant for us, and it's better to do things different ways. That's probably really vague, but unless you're really into the design of floating point units, it's hard to kind of pin down and give you concrete examples. But if there's anybody who is, I'm more happy to talk about the detail of that. SymFPU on float 32 and float 64, which is effectively single and double precision, we have reasonably good evidence to believe that it is correct. There are some known bugs in some more obscure formats. So if you want, a floating point format where you've got 200 bits in the exponent and like 3 bits in the significand, that may not work. It will have the defensive coding in the library means it should crash and stop things rather than give you incorrect results. So I'm working on fixing those, but it's kind of hard. It's difficult to justify because at the moment nobody wants to use them. The vast majority of people want to use float 32 or 64. If you have a use case for a more obscure format, please let me know. I'd love to help, but at the moment it's like, yeah, we'll fix it at some point. So the basic idea behind why SymFPU, I think, is a good set of encodings is most floating point operations work like this, that they have an unpacked, they have a packed format. So that is the bit vector that you write, you have in memory if you've got a single precision float, or you write with FP and then like we were doing earlier. So that's what you start with and that's what you end up with. But most operations, so what actual hardware does and what our encoding does, the first thing you have to do is you have to unpack that. So there's a way of encoding this is not a number. Actually, you probably want a single flag saying this is not a number. You probably want flags for infinities. You want to separate out the significand and the exponent is biased, and the significand tends to have the leading 1, because as they're all numbers between 1 and 2. Well, in that case, you don't need to write 1. So it's omitted. So there are always little fiddly details. So first you get rid of those. Then you do the actual operation, and that winds up with a floating point number in a larger format. And then finally you round. So the circuit looks like the semantics, and semantics looks like the standard. And then at the end, you pack it back up. So one of the tricks that SymFPU does is that if the next thing you do after you're going to pack is unpack, then it forwards the unpacked format. And so you save this repeated pack and unpack and pack and unpack. I think SymFPU is the only encoding that does that. And it doesn't sound like it would save you a lot, but what it means is you can make the pack and unpack quite large and expensive because you rarely need to do it. And so sometimes there are trade-offs where if you make unpack more complex, you make the operator simpler. And so we've done a lot of those kind of trade-offs. So yeah, the unpacked format, yeah, there's a lot of choices you can make there. And again, if people are interested in the details of floating point units, I'm happy to talk through them. But for everyone else, let's keep going. So this is about the point in the talk where everyone's like, oh, could you just show us one of these encodings? And I'm like, yes, but. So let me just switch. So this is a floating point adder. So every little node shape we have here is some kind of gate or operation. Now, this, I think this is, A plus B equals constant. I think this is the equality part. So the lines are effectively a circuit connecting it. And the coloring, so these purple lines are the exponent. The blue lines, I think, or the cyan lines are significant. And the coloring of the nodes is how expensive they are. So let's zoom in and have a look. Basically, this is unpack. This is your unpack logic. This is the actual add. That's the operate. I think this is the rounder. And this is to put it back together afterwards. So this is about 30%. Let's have a look. So this is, I think this one here. Sorry. No, that's the highest level of detail it will render it at. So this one here, I think, is the actual addition itself. And so you've got ladders that kind of renormalize numbers. You've got splits on which is the biggest number. So you put that first, so you subtract, so your result should always be positive or zero. This is just unpacking, making flags. Most of this is pretty cheap. But yeah, so this is the kind of scale of thing we're talking about. This is one addition. So this is why, if you're going to take this route, you need a really good bit vector solver. And SymFPU means we can kind of skip this packing part, but that's still an awful lot of bit vectors to look at. Where are my slides? We've got a question on the chat. Oh, okay, that's one we've already talked about, local search. So yeah, I don't, again, I'm happy to talk people through details of the code if they want, but generally I don't put it in presentations because that's the sort of scale of thing you're talking about. Correctness. So given that we're building these sort of things, you might ask, well, how do you know they're right? So this is our ETAPS paper from a couple of years ago. We went through a very extensive verification process for trying to demonstrate that the circuits that it generates are actually correct. As I say, we're still not completely at the end of this, but it's been in use and in the wild for a couple of years now. And we've even had some groups of people trying to fuzz it and find issues. And I'm not sure that we've had any problems reported in the formats that we've done the verification on, but it is worth thinking about, and increasingly it's getting to be an interesting research area. You know, if we're building SMT solvers, you know, if we have SMT solvers that we're using in verifiers in important applications, how do we know that the SMT solver is correct? And I think this is the work we did for this, and it's documented in the paper. I think this is probably the largest and most comprehensive sort of verification of attempt of an SMT solver for any project so far, I think. But yeah, in some ways, if you are interested on the sort of software quality and software testing side, SMT solvers are, in principle, a really good thing to work on because you've got multiple different implementations of the same thing, all that implement, you know, have a very clear spec of what they implement. If you're going to get into doing it, though, do be a little bit careful, because there have been groups who've written fuzzing tools for various SMT solvers and have then, you know, sort of flooded the issue tracker of various tools with like, oh, look, this combination of flags doesn't quite work. And it's like, well, yeah. So if you're interested in software testing, you know, how do we know SMT solvers are right is a fascinating question and a really exciting one to work on. The one thing I would suggest is talk to the solver authors first and work with them. Don't just dump like 400 issues on their issue tracker and then kind of ask if they could just tell you which ones are actually important. Right, so performance. So these are some slightly old numbers for a reason. Sorry. So these are from kind of about when we published the paper. And so these are various different benchmark suites. Most of these, I think, now are in SMT-LIB. These are a variety of different solvers. So this is Altergo, Calibri, this is CVC4, which we were working on. This is GoSat, which is what I was saying about numerical methods. MathSat with the ACDL, so this kind of combination of CDCL and interval reasoning. So Sonalar. So Sonalar is interesting, and again, shout back to Conway's law. Sonalar was written by one PhD student, and he's still, like years later, is still outperforming us on one set of benchmarks. This is Z3. This is one of the Chicago 2014 paper on reducing the size of floats in it. And this is the virtual best solver. So what we've done is we've reported the percentage of each benchmark suite that solver can solve. So interesting points here, and we've also bolded if for everyone apart from if we bolded the highest individual result apart from VBS, virtual best. And I'm quite proud to say that we've got, you know, almost all of the categories we're winning on. The ACDL, that's previous work from a few years, and there's still a few we can't beat, which is a bit embarrassing, but it is as it is. Yeah, I mean, there are also cases like where, you know, Calibri implements a radically different technique, and, you know, sometimes we way better, other times it is incredibly close. And sometimes they're ahead of us. Like, so this is one of the reasons that I sort of said, you know, talking about which solver do you use, and use all of them, because in every case, the virtual best solver is best, and often significantly better. Here, you know, the best individual solver, we're solving barely 2/3 of it. Here, we're up on 4/5. This is why you want to keep your architecture flexible, because the VBS is best. Anyway, these results, we put them in the paper and got very kindly accepted. And okay, well, that's good, isn't it? You know, produce a really fast system. And for 2 years, I won the majority of the floating point content tracks at the SMT competition. The ones I didn't basically went to Colibri, who are great people. So yeah, and then this year the results came out, and I don't think we won a single one. But I'm very pleased to say why. And the reason is that Bulector picked up the SymFPU library, integrated it, and because they have a very, very strong bit vector solver, completely wiped the floor with us. So again, maybe this is some sort of point about integration and trying to make sure your tools work with other people, because then even though my entry lost those tracks, I still feel I can claim a little bit of a moral victory for that. So anyway, conclusions. Right, so open problems, new approaches. So he talks about those sort of 4 areas, and, you know, in some ways these results are good. You know, published, we got the fastest solver, or at least we had, and now Bulector's faster. In other ways, they make me really quite deeply concerned and disappointed, because, you know, is this really the best we can do? Is it really the case that the best possible thing, despite like a semantics that's written about real numbers, is honestly the best way we can reason about floats to produce a circuit and just be like, yeah, this is kind of what hardware does. Schlam. Is that it? You know, I mean, like, thanks to people like Armin, we've made some absolutely great progress on like SAT solvers. There's a load of other people involved there as well. But surely we must be able to do better than that. Like, isn't it crazy that the best we can do? We've got, you know, we're trying to work with real valued numbers, and then we're turning them into bits. That's insane. So new approaches. There must be other ways to solve this problem. certainly on the interval side, Calibri do a great job with propagation, but their search is not great. There's almost certainly a way of combining what MathSat ACDL and Calibri do, and that combination will be very, very powerful. That would work. The axiomatic side, there must be a way of expanding those real axioms and then doing something with reals. I'm convinced it must exist. On the numerical side, there's got to be a local search technique that works for this. Like, you can't really, is it really the case that just reducing everything to circuits is honestly the best thing we can do? I mean, it's crazy. Like, it's just a huge, great hammer brute forcing the problem, but we must be able to be smarter than that. Which then, like, is also a question about mixed real and float, because, and I guess this is kind of bringing us a little bit full circle, where I said that, one of the advantages, why SMT? Well, it means that we can pin down our interpretation, and we can have these theories, and each theory is a world unto itself. You do a specialized decision procedure, and that's fine right up until the point you want to mix different theories, and the logics allow it. The logic, if you've got QF, FP, floating point, NRA, nonlinear reals. So then you can mix floats and reals. So you can have your algorithm written in floating point and your spec written in real. And you can ask, is my computation sufficiently accurate? The problem is, though, that your float part will go to the float theory and your real part will go to the real theory. How do you pass information back and forward between them? And that's an algorithmic problem. It's also a software infrastructure problem. And, we've made a lot of progress on SMT solvers that work by separating out each theory and having it work on them independently. Maybe that's Conway's law again. Maybe it's one student per theory. But yeah, how do we do this kind of cross-theory reasoning? Open question. And the same goes for bit vectors and mixing from real. Because right back at the start, when we had that, at the start of this session, we had that bit of code, really what we want to do is be able to take that piece of code, convert it to, well, some of it's going to be a bit vector, some of it's going to be a float, and then just put a real valued spec on it, saying it samples at n points between these two. At the moment we can write that problem, we can't really solve it efficiently. Trig functions. This is another horrible, horrible mess. If you want to verify control code, you almost always wind up working with trig functions, because at certain points someone wants to work out how far you need to turn a wheel or a rudder, or we're flying a drone and how much do we, you wind up with trig. The state of numerical computation of trig functions is an exciting mess. What we should do with them in solvers, also, of course, there are challenges with scalability. We build these, because this bit blasting seems to work. It's kind of embarrassing that it does work that well, but because of that, we produce some really, really big problems for a SAT solver to solve. And it's great that we can just kind of ask Armin, but we really need to work on scalability as well. So if this has inspired you, there are a bunch of really interesting problems here. Right, so conclusions of the whole thing. Tool support, I've sent Sarah the slides. You can go back and have a look at that example. I think last time I really stared at it, I think I found 7 different issues and 7 different weirdnesses why it wouldn't meet its obvious spec. But the fact that, you know, the fact that you can look at this and just be like, is this right? Okay. We can't have humans checking this kind of thing. It's just not a scalable or a viable option. We need tool support. And if we can use an SMT solver to do it, that means we can separate out generating the formulae and solving them. And hopefully we can build better tools. Because we've added floating point, we've added a theory for floating point to SMT-LIB, we have a standardized way, we've got standardized benchmarks, including those benchmarks with massive suite of correctness tests. Just basic, is your solver giving the right answers? That's part of that correctness process I was talking about, and those have been incredibly useful. There are a number of solvers off the shelf. If you want to build bit blasting solvers to do float, again, that's now a component off the shelf. But we are a long way from having this handle really big things, and that's kind of, I guess, the link to what's happening tomorrow. So where I said, you know, I really think we should be able to do better than just circuits, because at a certain point it runs into scalability problems. Well, Guy's going to be talking about neural networks and the verification of neural networks, and in his specific case, even though the systems are actually mostly implemented in float, he's got a whole bunch of algorithms that work on real. And so that, to me, that's kind of like, it supports this view. You know, there really are a bunch of problems that are, you know, we can come up with specific solutions that are better than bit blasting, but can we make those more general? So Guy's going to talk about that. He's going to talk about neural networks in general and where we go with this. I want to get to a point where we could just feed the whole network in floating point through the solver. We're not there yet, but I don't know, maybe with your great ideas, maybe we will. Anyway, thank you very much. I've been Martin Nick's brain. You've been extraordinarily patient. My thanks to Keith for that joke. I think that's the end. That's pretty much everything I wanted to say. I'm happy to take questions now, or we can go to Discord, or if you're one of the people watching this on YouTube in the future, I guess you might just have to email me. So thank you very much, and I think I'll stop at this point. Kind of hoping Sarah will take over now.